There's another question that we come to, and that's if you look at that example where we had a central carbon with an oxygen and a chlorine, how come the oxygen was the one that formed the double bond? Why not one of the chlorines? Well, we can make a sort of an argument that, well, the chlorine is more electronegative, and so it's less likely to give up an electron. It's less likely to donate an electron. It's very greedy. There's a more systematic way of doing this, and that is to look at the concept of formal charges. So the way we calculate a formal charge, and this is not the same as an oxidation number. It sort of looks like it because we're putting like a plus on it, but an oxidation number is sort of like the total electrons that belong to the atom. If we were to divvy them up among the atoms, like how far above or below the neutral element it is. And here is how much above or below is it than the normal valence state of that electron. So what we do for the formal charge, we take the number of valence electrons of that atom. And the formal charges are assigned per atom. We subtract out the number of non-bonding electrons, and then we subtract out half of the bonded electrons. Those are only shared, so they only count for half. So things that you have to have. So the sum of the formal charges has to equal the net charge. If it doesn't, you did something wrong in assigning formal charges. What you want is and to look for what arrangement of formal charges is best, you want to have as low numbers as possible. A +2 or a -2 is bad. You want to have, if at all possible, only plus ones and minus ones, and you want as few positive and negatives as possible. If you have 1 + 1 and 1 - 1, if you have one resonance structure with that, it is not nearly as stable as one with no formal charges total. And then if you have to have formal charges, you want the negative charge to be in the more electronegative atom. So let's start with, so those are the things we want to look for. And then one other thing is that you want the like charges separated. If you have two minuses, the minuses with the two pluses should be as far apart as possible. So, okay. So let's look at oxygen. Let's calculate the formal charge for the structure. Now notice the structures are the same, so we don't need to do it for both structures, but let's just look at one of these. So let's calculate the formal charges. Here we have 6 is the, switch to a different view. For this, we have 6 is the valence electrons for oxygen, -4 that are on lone pairs, -1/2 the number of electrons that are in bonds, so that would be 0. So this atom has a formal charge of 0. This one here at 6 - 2 - 1/2 times 6, because there's 3 bonds. So that is actually a 6 - 2 - 3 + 1. And then here we have 6 - 6 - 1/2 2. This is a -1 formal charge. So in this case, we there are no way, these are the two possible Lewis structures we came up with. Both of them have have a formal charge. So actually, if we looked at the resonance structure of both of these, this would have a +1, and this would have -0.5, -0.5, if you consider both of these structures together. Because in both structures, the center one has a +1, and they alternate which one is 0 and which one is -1.